Hi, thank you for watching. I'll be talking about the testability of relations between permutations. This is a joint work with Oren Becker and Lubotzky. We'll start with a basic instance of the sort of problem we're interested in. Suppose that we're given two permutations A and B, both over the integers 1 to n. We'd like to test whether these permutations commute. Namely, is it true that a of b of x equals b of a of x for all x? It's convenient to view the two permutations as a directed graph over the domain. So for example, for n equals 5, we have a graph with 5 vertices. The blue and red edges represent the actions of A and B respectively. So each vertex has one outgoing edge and one ingoing edge of each color. What we're looking for is an algorithm that queries a small number of edges of this graph and distinguishes between the case where the two permutations commute and the case where they are far from commuting. More formally, an algorithm is said to be an epsilon tester for the relation xy equals yx, where x and y stand for two permutations, if it satisfies the following properties. First, the algorithm should be complete. That is, if a and b compute, the algorithm should accept with high probability. Second, the algorithm should also be sound. If a and b are epsilon far from commuting, the algorithm should reject with high probability. By far from commuting, we mean that if one wants to transform A and B into a new pair of permutations, A prime and B prime, which does commute, then one needs to change at least epsilon n entries of A and or B. Finally, we want the algorithm to be query efficient. Namely, the algorithm is allowed to ask k questions of the form what is A of x or what is B of x, where k may depend on epsilon but not on n. Now, if for every epsilon there exists an epsilon tester, then we say that the relation xy equals yx is testable. So, is this relation xy equals yx actually testable? So, if you're trying to invent an algorithm to test whether two permutations commute, the following would probably be your first attempt. This algorithm, which we call sample and substitute, samples k vertices uniformly at random and checks that A and B commute on these k vertices. For a given vertex x, this can be done with 4 queries, since the algorithm only needs to query b of x, a of b of x, a of x, and b of a of x, and check whether a of b of x is equal to b of a of x. If A and B commute on all of the k-sampled vertices, the algorithm accepts, otherwise it rejects. Now, sample and substitute has perfect completeness. That is, if A and B actually do commute, the algorithm is guaranteed to accept. The question now is, what about soundness and query efficiency? It makes sense that the larger k is, the more likely it is that the algorithm would be able to detect that A and B are epsilon far from commuting. The question is whether k can be taken to be a function of just epsilon while achieving the epsilon soundness condition. Fortunately, a theorem of Argentjevo and Paunesco yields a positive answer. So their paper is in group theory and does not directly address this question of testing whether permutations commute. However, after we reformulate it into property testing language, the result says that for every epsilon, there exists some k such that the sample and substitute algorithm with k repetitions is an epsilon sound tester for the problem of committing permutations. Since k does not depend on m, this is also a query-efficient tester, and we conclude that the relation xy equals yx is indeed testable. Now, furthermore, the result of Oren, Becker, and myself says that k can be taken to be a polynomial in 1 over epsilon. So we conclude that not only xy equals yx is testable, but the necessary number of queries is at most polynomial in 1 over epsilon, which is good. Okay, so now what about other relations? We'd like to generalize what we just did to relations between permutations other than commuting. So as another example, take the relation xy squared equals yx. Namely, given two permutations, a and b, we want to test whether it holds for every x that ab of x equals ba of x. Now, by a rather deep result of Becker, Lubotzky, and Thom, again reformulated to property testing language, this relation also turns out to be testable by a suitable version of the sample and substitute algorithm. Namely, this algorithm just tests the relation ABB equals BA, again on several randomly sampled vertices, and accepts if the relation holds on all of these vertices. And this turns out to give a good guess on whether the permutations are actually satisfy the relation or are far from satisfying it in the global sense. Now, we can also consider systems of several relations and relations on more than two permutations. So, for example, the Urgencheva-Paunescu result that I mentioned before actually generalizes to show that sample and substitute can also be used to test whether three given permutations all commute with each other. And in fact, it holds for any fixed number of permutations. Okay, so up till now, we've seen several examples of relations that can be tested by the sample and substitute algorithm. Now, for reasons having to do with the group theoretic origin of this problem, such a system of relations is called stable. In the present work, we're discussing testability of systems of relations beyond the sample and substitute algorithm. So, for example, we show that the relation xy squared equals y to the third x is testable, but it's not stable. In other words, sample and substitute is not an adequate tester for this relation between permutations. However, there is some other algorithm, which we will soon describe, that does manage to test this relation. We also show that some other relations cannot be tested by any algorithm. So this includes some actually rather simple examples. So the relation x squared equals y to the third, and also the relation xy squared equals y squared x, both of these cannot be tested by any algorithm. Also, the system of relations xy equals yx and xz equals zx, that is, we're given three permutations, and we need to decide whether the first one commutes with each of the other two, but y and z do not necessarily need to commute with each other. This is also not testable by any algorithm. So let's illustrate this landscape more graphically by a Venn diagram. So first we have the stable systems of relations, which are testable by sample and substitute. The stable systems are contained in the class of testable systems, which contains them, but also contains relations such as this one, which are testable by some algorithm, but not by sample and substitute. And finally, we also have systems of relations that are not testable by any algorithm. Also, even after the present work, the placement of many systems of relations in this diagram remains an open problem, and you can see several examples here. Now, before turning to describe our results, I'd like to spend a couple of minutes to describe what was done in previous works and compare their approach to ours. So previous works on this subject only studied the notion of stability, which has a very natural group theoretic motivation. And these works think about relations between permutations solely from a group theoretic perspective, without going into any of the algorithmic notions that I gave at the start of the talk. I should mention that in recent years, this field of group stability is seeing a lot of action, and there's really been an explosion of works in recent years. Now, most of these works describe certain criteria by which one can determine whether a system of relations is stable or not. So they try to place different systems of relations in this Venn diagram, either inside the circle or outside of it. Now, the main paradigm in all of these works is to study the testability of a system of relations E by associating E with a certain group. Namely, if E is a system of relations over a set of variables S, we define the group gamma E as the quotient of Fs, that is the free group generated by S, divided by the system of relations E. Then we can study the stability or instability of E via properties of this group gamma E. Now, to illustrate this paradigm, let's go back to our original example of testing whether two permutations commute. So here S consists of two variables, x and y, and E is the single relation stipulating that x and y commute. The group gamma E is then the quotient of the free group over the two generators x and y by the commutator of x and y. And this is isomorphic to the group z squared, where z is the additive group of integers. Indeed, Fs consists of all words consisting of x's and y's and their inverses. Now, dividing this free group by the commutator means adding the relation that x and y commute to the free group. Now, if you think about it, given that x and y commute, the only thing we need to know to describe a word consisting of x's and y's is two numbers, how many x's we have in that word and how many y's we have in that word. And this gives us a natural embedding into z squared. Now, the Urgencheva-Paunescu theorem in fact says that whenever gamma E is in a abelian group, E is stable. Now, since z squared is abelian, it follows that the relation of two permutations commuting is indeed a stable one. Last, I should mention that this whole paradigm is supported by one crucial theorem. This is that the stability of E is really a property of gamma E. That is, if we have several different systems of relations which are all associated to the same group gamma, then either all of these relations are stable or all of them are not stable. In this sense, stability is actually a property of the group gamma E rather than a specific system of relations that is a presentation of gamma. Now, compared to these previous works, our work first defines and studied the notion of a testable systems of relations and permutations. Like these previous works, we try to identify criteria, but here it's not for stability, but rather for testability and non-testability of a given system of relations. And it turns out that this can also be done by looking at the group gamma E. And this is cool because this notion of testability has been motivated by an algorithmic question, a rather natural one. But it turns out that it's also naturally meaningful in the group theoretic view. Okay, so let's turn to describe our results. A basic notion that we'll need is the set Sol E, consisting of the solution graphs for a given system of relations E. I'll explain what I mean by Sol E by an example. So again, in the case of the relation xy equals yx, this is an example of a solution graph. So here each vertex has exactly one ingoing and one outgoing edge of each color. And the blue and red actions commute. That is, walking blue and then red always brings you to the same place as walking red and then blue. So this is really a solution to the relation xy equals yx. Now the set of solution graphs for xy equals yx, including all graphs with this property, including not just finite graphs, but also infinite graphs. Informally, our main positive result says that for any system of relations E, if the set of solution graphs Sol E is very non-expanding, then E is testable. On the other hand, our main negative result says the opposite. If Sol E is very expanding, then E is not testable. Next, we also show that there is a specific algorithm more powerful than sample and substitute, which is universal. This algorithm is universal in the sense that any testable system of relations is testable by this specific algorithm. And finally, we show that the testability of the system E only depends on the group gamma E. And this is analogous to the corresponding classical statement about stability depending only on gamma E, so this holds for testability as well. Okay, so let's go into more details about our main positive and negative results, which relate expansion of the set of solution graphs with testability. To state these results, we need to define two notions of the expansion of a graph. First, the isoperimetric constant of a graph is the infimum over all finite vertex sets X of the isoperimetric ratio of X. That is the ratio between the number of edges going out of X and the size of the set X itself. Now note that a finite graph always has isoperimetric constant 0 because one can take X to be the entire graph and then there are no outgoing edges. On the other hand, some infinite graphs, such as the regular infinite tree, have the positive isoperimetric ratio. Now, the second notion of expansion is the more familiar Shear constant. This is defined only for finite graphs. And the Shear constant is the minimal isoperimetric ratio over all the vertices consisting of at most half the vertices in the graph. Now, in these terms, our main positive theorem says the following. Suppose that every solution graph of E has isoperimetric constant 0. Again, this trivially holds for the finite solution graphs, but not necessarily for the infinite ones. Then, in this case, E is testable. And this theorem has an equivalent formulation in group theoretic terms. If the group gamma E is amenable, then E is testable. Amenability is a very important property pertaining to the geometry of the Cayley graph of the group. Now, since many groups are known to be amenable, we can conclude the testability of many corresponding systems of relations. Our main negative theorem is somewhat the opposite of the main positive theorem. So let F Sol E denote the set of solution graphs that are also finite and connected. Suppose that this set F Sol is itself infinite and that is an expanding family of graphs. That is, that the Shear constant of all the graphs in F Sol is bounded away from 0. In this case, our theorem says that E is not testable. And again, this theorem is also has an equivalent statement in group theoretic language. So here the criterion for non-testability is that the group gamma E have what's called property tau and also has infinitely many quotients. Property tau is a well-studied group property, and in particular it is implied by the more famous property T. So again, we know of many groups which have property T and thus also property tau, and these yield concrete examples of non-testable systems of relations. Now, the proof of these positive and negative results goes through the notion of our universal testing algorithm. So the way to prove these results is we first show that a certain algorithm that I will now describe can test any testable system of relations. And then to reason about whether a certain system is testable, we only need to determine whether this universal algorithm manages to test it. To describe the universal algorithm, we need to define what is the local profile of a graph. So recall that our graphs are directed graphs with colored edges. The R local profile of a given graph G, and this would be a finite graph, is the distribution of a random ball of radius r in that graph. That is, we sample a uniformly random vertex x and consider the distribution of the radius r ball around x up to isomorphism. And this distribution is called the R local profile of G. Now, a universal algorithm called local statistics matcher does the following. Given a graph G, our goal is to determine whether G is a solution graph or far from one. So to do that, we first sample k vertices of G at random. Then we compute the ball of radius r around each of these vertices. This yields a certain distribution which we call the empirical, which approximates the R local profile of the input graph G, just because to obtain the empirical we sampled from the actual distribution, and by taking enough samples we get a relatively good approximation. So now we check if the local profile of our graph G, or our approximation for that local profile, matches that of any solution graph. If there is some solution graph which locally resembles the empirical profile of G, then we accept. Otherwise, we reject. Now, our theorem says that local statistics matcher is universal in the following sense. If a system of relations E is testable, then for every epsilon there exists some parameters k, r, and delta such that local statistics matcher with these parameters is in fact an epsilon tester for the system of relations E. Okay, so these are our results, and now I'd like to briefly discuss some further research. So first, this is a fresh subject, so there are tons of interesting questions to think about, and if this seems interesting to you, I recommend reading the open problems section of our paper. Now, I'll mention a few of these open problems right now. So first, a straightforward major goal is to complete the Venn diagram that I showed before, namely find some convenient characterization which allows us, given a system of relations E, to determine whether it is testable or not. Now, another natural question concerns the dependence of the number of queries on epsilon. So with several exceptions, most known positive results are of the form, for every epsilon there is a k number of queries, which allows us to test, to construct an epsilon tester, but we don't actually know what is the dependence of k on epsilon, and that is something that is interesting to study. Next, let's consider time complexity. If E is a stable system of relations, then we're good, because the time complexity and query complexity of sample and substitute are essentially identical. However, in the case of where E is testable but not stable, a straightforward implementation of local statistics matcher is very inefficient because it requires going over all the solution graphs, which can take an exponential amount of time. So it's interesting to see which systems of relations allow a more efficient implementation of this algorithm. And finally, another question is, what can we test if we relax the definition of testability and actually allow the number of queries to depend on n by some modest function, which has to be sublinear, because linear dependence on n makes the whole thing trivial, but any sublinear dependence might be interesting. Okay, and that's it. Thank you very much for listening, and see you all at FOCS. Bye-bye.